think we are ready to start. Please take a seat. So we can start this observation session, and we'll have as a keynote speaker Joanna Teske from Carnegie, who is going to tell us about the perils and promise of observations to characterize rocky exoplanets. Please.
All right, starting my timer. All right, yes, thank you everyone for being here this afternoon, and to the conference organizers for the opportunity to be here to give this talk. I'm mostly talking about other people's work, but I have some contributions from my JDUST team, so I also want to thank them as well. When I was putting together this talk, I remembered a scientific communications workshop that I took as a graduate student, which recommended a specific narrative arc for talks, which is the hero's journey, where you are faced with a problem, you encounter challenges along the way, but ultimately the hero, the scientist, succeeds. And so that is how I've sort of structured my talk, with some caveats. We will encounter some interesting challenges along the way. I will talk about both promises and perils at each stage. However, there are two important differences. One, I am not the hero of this journey. Everyone else in the audience is. Like I said, I'm mostly not talking about my work. And we don't have a happy ending final conclusion. But actually, what I'll show at the end is, I think, some things that I'm excited about that we've learned, and then opportunities for learning more, which is why we're in this field. And so these are my biased takes on these topics. It's absolutely not comprehensive, so I apologize if I've left out some of your work or your favorite work. All right, so starting from the top there, I broke this on into kind of three main subsections. So the first observational subsection that I'll talk about is measuring planet densities and bulk compositions. And in this talk, in the upper right corner, I'll highlight some talks and posters that also touch on these topics, some of which we've already heard. So starting with perils, things to be aware of or maybe wary of. This is an obvious point, but I think it's really worth driving home for anyone who is not doing radial velocity observations. Getting the masses or minimum masses of non-transiting exoplanets is very time intensive, especially when you're going to longer orbital periods and more temperate temperatures. So this is a plot I made a few years ago, just collecting these measurements from papers. The bold circled symbols are multi-planet systems, and you can see the general trend as you go to smaller and smaller planet masses, you need more and more RV observations, and that takes more and more telescope time. Just illustrating this with a few specific examples, we have the closest M-dwarf transiting planet system, LTT 1445A. It has two small transiting planets. This required, for this publication by Judd Winters, 136 RVs from 5 different RV instruments around the world, resulting in something like 40 hours on sky. That is on sky. That doesn't account for weather losses and all the nights that didn't work out. And that results in something like 10% errors in mass for these transiting planets where we know the period a priori. These are from TESS. Another TESS example, this multi-planet system, which I think still has the record for the smallest planet mass measured with just RVs, not UTVs. I could be wrong with that. And again, with this multi-planet system, we're talking over 200 radial velocity observations with 2 highly precise instruments, resulting in almost 80 hours on sky. And for this smallest planet, planet B, that's still only about a 40% accuracy or precision in the mass measurement. So this is very time intensive. This is going to be a major theme in this talk. Stellar activity is often a hurdle in measuring the masses of these small planets. And for the transiting planets, their bulk densities. And this is only going to increase in being a problem as our precision in measurements, mass measurements increases or gets better. And so this is a figure, these are both figures from a collaborative effort that I was part of called the NASA NSF EPRV, Extreme Precision RV Working Group. And the plot on the left is showing that green line looks like a straight flat line, but it actually is supposed to represent the Earth's RV signal on the sun. So there's a 9 or 10 centimeter per second wiggle in there, but plotted over top in gray are the solar observations. So there's a solar feed to the HARPS North telescope. And so that's what the sun is doing in gray versus the Earth. And so this illustrates the challenge in detecting temperate terrestrial planets around sun-like stars. And sort of the different types of stellar variability are illustrated on the right plot in terms of the different time scales, and then the RV effect in meters per second, which is typically the unit that we use. Note that the y-axis is in log units. And so the Earth is in blue in this point at about 0.1 meters per second, but there's all sorts of types of stellar activity that could mask or mimic a planet signal of Earth amplitude, or even, maybe 1 meter per second or slightly higher. A technique that has been used a lot in recent years to try to mitigate or model stellar activity has been Gaussian processes. This is a very powerful technique. I'm not going to go into the nitty-gritty of it, but the point I want to make here is that it should be used with caution. So this is just an illustrative example from Sarah Blunt's paper last year. It's a great paper. I encourage you to check it out if you're interested in this problem. And she's looking at a pre-main sequence star that's fairly active. It does not, as far as you know, have small planets. So this is just to illustrate the point of caution with Gaussian processes. She's reanalyzing observations that were previously published of trying to measure the masses of the planets around these stars. And basically, in this paper, illustrates that this Gaussian process probably is overfitting the RV observations. So in this plot, she's illustrating that if you look at the residuals, which is in the histogram plot on the left, the residuals for the HARPS North measurements are, strongly peaked and narrow, whereas the RV residuals for the other two instruments are widely spread out. She also does sort of not leave one out, but remove some of the HARPS North data and tries to use the same model as was trained on all of the data to then predict the HARPS North RVs, and finds that it's not able to do that. So these are signs that the model is overfitting. And just to illustrate that, the right plot is the Keplerian signals of the planets, and the gray is the Gaussian process stellar activity model. And you can see that during those gray windows of observations, it's changing very drastically, and sometimes on the same amplitude as the Keplerians. So the point that Sarah makes in her paper is we really need to validate these different activity modeling techniques on stars with well-studied activity signals, and ideally independent measurements of the stellar activity like photometry. All right, even if you get all the telescope time, measure super precise mass, you still might not know the composition of your planet. And that's because there are additional things that can come into these uncertainties. So we've heard a little bit about water worlds. This is a plot from James Rogers' paper last year where he showed that these water world, potentially water world planets can also be fit with just a rocky planet with a hydrogen helium envelope that has evolved over time. Caroline and Tim's paper from 2021 goes into more detail about how you can store water in the interior of the planet. And this has implications for then the water mass fraction of the planets. So this is a great paper, but I wanted to point out that looking at their predicted mass radius curves and then looking at the observed points, there's still, for each planet, potentially multiple possibilities in terms of which regime it's in, and also the water fraction. And then I think we'll hear more later this week about some of the uncertainties around just the extrapolated mass radius relations into the regimes of super Earths and sub-Neptunes. And so this is a plot just showing that the blue is the measured mass radius relation predicted from an iron equation of state determined experimentally. And if you extrapolate that up towards larger planets, that can result in some uncertainties in your interpretation of the iron content of those planets. All right, I need to speed up. So those are all the bad news things. good news things, we have many PRV or EPRV spectrographs that have come online recently. I'm just showing a snapshot here. There are more. And what's exciting is many of these have solar feeds, and so they're observing the sun as a star, the disk integrated light. And we can look at simultaneous observations from different instruments of the sun and use those to try to both better understand the sun's variability, because we can actually resolve features on the surface through different imaging, and learn about what's happening with the instruments. And so, for example, in Lili Zhao's paper, here in these plots, each one is showing on the y-axis one instrument, and then it's plotting the RVs versus the other instruments. And you can see this little oscillation in the HARPS RVs, and that's probably due to dust on the transparent dome inducing differential extinction. So not something in the star, but something in the instrument and the observations themselves. So we can start to disentangle that. Also another paper from Lili where this is investigating a bunch of different techniques for trying to model RVs. This is one example where she shared data for this one star with many different teams, and they used different techniques to try to measure the RVs and mitigate different types of stellar activity. Again, don't have time to go into the details. This is a fascinating paper if you're interested in this topic, but I wanted to highlight one of these techniques, which maybe we'll hear about later more this week, I'm not sure, that basically instead of using all of the lines in a stellar spectrum to model the radial velocities, you choose lines that are shown to be less sensitive to stellar activity based on the depth of the line, and that can reduce your the RMS in the derived velocities. So I think this is one example of a really promising technique. Also, just briefly switching gears a little bit from mass measurements, but I think constraints on bulk compositions of rocky planets can also come from the other end after the stars are off the main sequence, looking at polluted white dwarfs. So Ali Doyle has done some work on this, looking at oxygen fugacity in these polluted white dwarf abundances, and showing that they seem to be at least as oxidized as the Earth, if not more. There are some caveats to this, which again, maybe we'll hear about more later this week from Claire. And looking at now abundance ratios, Harrison et al. Used a model trying to match these abundance ratios, starting with sort of a pristine protoplanetary disk composition, although varying that composition, and then adding on different differentiation or fragmentation mechanisms. And from that, they're trying to distinguish whether the accreted material onto polluted white dwarfs could be core-rich, crust-rich, or volatile depleted. So again, just a snapshot of some of the interesting things, the promise of constraining bulk compositions. All right, very quickly, host star abundances. This is where I've done some work in my thesis. I don't really see a way to get around this peril besides just getting more high resolution and high signal to noise data. Some of these lines and stellar abundances that we're really most interested in are weak. They're blended lines, so you really have to be careful about how you're constraining the abundances of the other elements that are contributing to, for example, this forbidden oxygen line. There can be NLTE effects, and this all becomes harder as you move farther away from the sun. Most of these stellar abundance measurements are made relative to the sun. And so as you move farther away, the uncertainties or the unknowns in the stellar models start to grow versus like a solar twin comparison, which have very high precision. This is also a topic of great interest. Does the stellar composition equal the planet composition? When is that true? I still come back to Caroline's paper from 2015, where she showed trying to just model the Earth's mantle silicon weight percent and different ratios, where we know the answer, right? For the Earth, we know these things. That's the green bar, and using the sun's information to try to put constraints on these as a prior helps you get closer to the right answer. So that's sort of a promise in terms of star equaling planet. And I think we'll also hear perhaps more about this week as well. Adebeki et al. From 2021 found with a model of the planet iron composition versus a stellar iron composition that there's not a one-to-one correlation, but some correlation between these two quantities. However, using a slightly more layered model for the planet composition, plot a common Valencia. Actually, they made a model where they can sort of switch back and forth between using a stellar composition and a planet composition so that they can be equally comparable. So in the top left plot, they basically took planet masses and radii, converted those into what they think the different elemental ratios would be, and then compared those to the Hypatia catalog, which is in red. And in the bottom plot, they took the Hypatia catalog stellar abundances and converted those into what they would expect for planet masses and radii. And the takeaway here is that the stars span a smaller range in these values than the planets do. So maybe there are at least some cases where the planet does not match the star. And this was also shown in a paper by Schultz et al., where in these plots, the purple histograms are the star's estimated core mass fraction based on, I think, the iron to silicon ratio versus the planet in orange. And again, they're finding limited ranges for the stellar distributions in purple, and that actually you need pretty different distributions between the star and the planet to statistically say that they are different. So this could be challenging even with very precise planet and stellar information. All right, so quick promise about the host star abundances. We've also heard a little bit about this topic. I think moving forward, starting now and into the future, there's this proliferation of all sky surveys and data-driven methods to measure stellar abundances. And so on the top, I'm showing the coverage of the LaMost survey, which I think has concluded at this point, and that was millions of optical spectra of stars. In the bottom plots, I'm showing Sloan Digital Sky Survey 4 footprint, and then the Sloan Digital Sky Survey 5 footprint, and this is the one that has just started. And this is going to be, I think, almost 10 million stars. And what's exciting for me from SDSS 5 in particular is that it includes near infrared spectra, H-band spectra at about 20,000 resolving power, which is great, as we heard, for M-dwarf abundances. And so this is an apogee spectrum. That's the infrared spectrograph showing all these lines that can be used to measure the M-dwarf abundances. They're not as contaminated by molecular features as in the optical. And at least in Diogo's paper, he's showing pretty good agreement with FGK dwarf abundances in C to O, magnesium, and silicon. All right, so this is the last main section, atmospheres. In this one, I decided to start with promise and end with perils. I don't know, that just felt better for this section for some reason. Maybe I was like wanting the good news first. So we saw this spectrum earlier today as well. We now are firmly detecting atmospheres of sub-Neptune exoplanets. There were some detections with HST, but this is really going to be coming fast and furious with JWST. So this is K218b transmission spectrum. You can see the strong contributions from methane and CO2. This is one of the first detections of methane in the exoplanet atmosphere, which was really exciting. And the authors also potentially detect dimethyl sulfide, DMS, and suggest that this combination of molecules is consistent with that Hycean world scenario, a habitable ocean underneath an H2-rich atmosphere. New work by my collaborator, Nick Wogan, suggests that maybe that there could be a slightly different explanation. So he is an atmosphere chemistry expert and finds that actually to explain the high level of methane, you actually need a biogenic or some other unknown source to maintain that methane at that level. Otherwise, it would be destroyed by photochemistry. Nick, being slightly conservative, suggests that instead of life, it could just be the explanation that this planet could be explained by just being a regular mini Neptune without a habitable surface, and that CH4 and CO2 is produced via thermochemistry deep in the atmosphere and then is mixed upward. So Nick submitted this paper. It should be on the archive soon. Different explanations, but definitely an atmosphere detected, which is exciting given the context that I'll talk about in a minute. We're also seeing new chemistry in these exoplanet atmospheres. So this is a phase curve from Eliza Kempton of a canonical small exoplanet GJ1214b. And so This is showing the planet all through its entire orbit. And the data are in the gray curve. And basically what this left plot is illustrating is to match those data, they need a highly metal enhanced, highly reflective atmosphere. Peter Gao also did some modeling just of the transmission spectrum part of this observation, and finds that those data suggest highly efficient haze production in the atmosphere, and or a kind of wider range of haze precursors than perhaps has been previously suggested. So I think this is really exciting in terms of kind of atmospheric chemistry in general, but also haze and aerosol experiments that I know folks are working on. Okay, so this isn't exactly atmospheres, but I think it's exciting. We can start to study the surfaces of very hot planets. We've heard about the TRAPPIST-1 planets and how whether they have atmospheres is still a little bit of a question, but at least for TRAPPIST-1b, it can be matched with a basaltic, metal-rich, or iron oxidized surface. In these plots, I'm highlighting the JDOS-T observed planets with blue shading, but interestingly, GJ1252b and LHS3844, which were observed by Spitzer, are also sort of consistent with this surface composition. The granite-wood and feldspathic surfaces aren't good fits, so that's already, I think, interesting. And this is actually a plot from Michael Zhang's paper, which out on the archive, I think last week. And so he has a spectroscopic secondary eclipse observation of GJ365b. Turns out when you have multiple points versus just one point, the story's a little more complicated. So I encourage you to check out his paper. The plot just wasn't as easy to explain. And what these plots also show is maybe the hint of some interesting trend. You can notice that at the lower temperatures, sorry, I didn't explain, these are radius versus the maximum highest temperature that the surface could be versus the normalized brightness temperature of the planet. And as you go towards larger planets, you're finding that ratio is actually decreasing, even though these planets are hot enough to melt all silicate rocks. And so maybe that points towards minerals being evaporated from the surfaces of these planet atmospheres. And so the hottest of these hot rocks might actually be great laboratories for telling us about how planet interiors and atmospheres are interacting. And so I think Anjali will talk about this. There's been great modeling work trying to estimate what JDOS-T would see with outgassing from a magma ocean into a primary atmosphere, or I'm sure Anjali will talk about her paper using a mix of rock vapor and volatiles evaporated from the surface. So this is a topic I'm super excited about. I think there'll be a breakout about this second day. All right, perils quickly. We have less clear evidence of atmospheres of smaller planets in the more rocky regime. This is one of the first publications from JDOS-T, basically a featureless spectrum of a Earth radius planet. The constraints on the atmosphere, it has to be tenuous or cloudy, secondary atmosphere, or it might just not have an atmosphere. From the group I've been working with, we have a slightly larger planet, but it's also consistent with, I mean, there are some bumps and wiggles in this spectrum, but statistically it's consistent with basically a flat line. And so we constrain it to have at least 250 times solar metallicity, if not higher. So it's a high metallicity atmosphere, probably. That's some knowledge, but we're not really detecting molecules. Again, stellar activity is coming in to ruin the party. From this paper by Sarah Moran and Kevin Stevenson and their team, they can't distinguish whether this upward slope for this small planet is indicative of a water-rich atmosphere or just unocculted star spots. Those scenarios might be more distinguishable with shorter wavelength data, but for now they don't know. And then we heard yesterday a lot about the TRAPPIST system. This is from Liminal 2023, where they have 2 visits for this TRAPPIST-1b transmission spectrum. The visits are not super consistent, as you can see, but both can actually be totally explained by stellar contamination, and atmosphere isn't needed to explain the observations. But this is definitely limited by the accuracy that we have on cool star models. So that's an area where more work is needed. And then again, for my group, one last point, we don't quite understand the sources of noise in the JDUST instruments. So this is by Nicole Wallach, paper that we submitted, where we have one transit observation of this planet. And this is with NRS, or excuse me, NIRSPEC, which has two detectors, which are observing the planet at the same time, but we are measuring different mid-transit times from each detector. That shouldn't happen. We're measuring the planet transit at the same time. And this system is particularly challenging because there are TTVs, and so we don't a priori know exactly what the mid-transit time should be. So using some detrending against engineering parameters, Nicole's able to resolve this a little bit, but this will be something to keep track of moving forward. How useful detrending with different engineering parameters are for JDUST observations. From this program that we're working on, we have lots of different systems. And so Nicole was able to make this plot that's showing in black the errors in ppm as a function of wavelength that we're getting on our observations versus what's predicted by Pendexo. And the positive way to think about this is we're doing okay, something like 1.5 or better times the predicted errors. But it's definitely a note of caution. And from Lily's paper, particularly when you're getting into the high metallicity regime around bright stars, many of which these small planet host stars are, the number of transits you might need to reach, say, a 3 sigma detection might be more than originally predicted. All right, so in the interest of time, I'm going to skip these last few points, but there are some papers that are really good at explaining why how you conduct your observations and construct your sample are important. And so if you're interested in that, I encourage you to check out Natasha's paper from 2023. The takeaways here are population studies. You really have to be careful of how you're choosing the subsample from the broader population because you don't want that selection to bias the results that you're inferring for the entire sample. So I'm happy to talk more about that in questions. And so just in summary, promise, we have lots of new instruments on the ground and in space that are giving us awesome, amazing data. It's just a great time to be an observer, I think. And this influx of data is being matched by increasingly sophisticated methods of analyzing it to really get the most out of it. And I'm seeing lots of collaboration between these different communities as evidenced this meeting. I think there's still ways to better understand JDUST data. Stellar activity is always going to be a problem, I think, / opportunity to learn more about the stars and the planets. And so far, I think we don't know whether rocky planets often have atmospheres or not. I think this will be one of the big questions that JDUST will help us answer. And then the last, so opportunities, I think, lots of work to do. And then the last point I made about carefully considering survey design and sample selection, especially as we're moving into things like the LIFE mission or Habitable Worlds Observatory, how are we going to be confident in our results? So with that, I'll end and take questions.
Thank you very much. Any questions for Joanna?
Wake up, wake up. You got to be ready for the breakouts.
Yep. Please.
Yeah, Brad Foley from Penn State. I'm just curious, with the problem of M-dwarf star interference and looking for atmospheric spectra, are there good ideas for how to deal with that? Is it something with, more observations can eventually be used to subtract out, or is it a worse problem than that?
Yeah, so I think more observations is always the answer. As we heard yesterday from Bjorn, I think in some cases, you're not going to be able to kind of build a statistical model to know when the best times to observe stars are. And so really then you just have to get lucky and just dedicate more observing time. I do think being a little bit judicious about which wavelengths you're observing at can also be helpful. And so, for example, the results I showed were just, I think, from 3 to 5 microns, whereas at shorter wavelengths, there's going to be more divergence between models. And so maybe specifically for some stellar types, we should first be looking at specific wavelength ranges, for example.
maybe a question from me on the noise characteristics of generality that you were showing, because the first time I was seeing things, I don't know if you can show them again. I had the impression that difference between actually observed and predicted, or maybe it was
This one?
Yeah. Okay. No, I was under the impression that it was mainly an offset, but how would you?
This one?
Yeah, maybe here.
Yeah.
It was more an offset. How would you? Could it be just for the noise that is underestimated, for example, or is it really some kind of instrumental noise source?
So we're more suggestive of a systematic noise source that we're not fully characterizing. I do think these predictions were made with maybe one older version of this Pandexo code, which is very popular for making these predictions. And so that might make the agreement a little bit better. But the bottom left plot, that's using the most up-to-date Pandexo calculation. And I think just once you're getting to the very high metallicity atmospheres, that's a new regime for all of us in terms of observations and modeling. And so that's where, we might need more of an adjustment.
Any more questions? Yeah. You can use your mic. That should be, yeah.
Hello. Thanks for the great talk. I have kind of a similar question to do with the uncertainties. Is there some trend in the difference between the predicted uncertainties and what you're getting based on the stellar type or anything else that we could be more aware of?
Yeah, we're very interested in that question. For this particular program, we have 12 planets, many with multiple transits, and around mostly cooler stars, but at least one or two like sun temperature stars. And so that's exactly what we'll be looking at as we're moving forward. These are all sort of preliminary analyses, but that's kind of a question we'd like to provide an answer for the community for future observations, for sure.
Yes.
So speaking of the solar abundances may not be the best reference for non-solar like abundance in terms of the differential analysis. So what would be your best suggestion, for example, to propose a reference abundance for M dwarfs?
Yeah, well, that's a good question. So you talked about using binary stars where the primary is an FGK stellar type and then the secondary is M dwarf. I think actually I'm a little bit more optimistic about that than in your talk. There have been several studies that have looked at binary pairs of stars, even just GG or KK type. And actually in most cases, they're quite similar to like 0.05 Dex level. And so I think M dwarf abundances relative to their primary star actually might be a way to get at the highest precision for M dwarfs. Does that make sense?
Yeah, somehow.
Okay.
Okay, any last question? Please. So let's thank our speaker again. We are moving to the breakout sessions. I just want to say before giving the mic to Amy, I just want to remind everybody that after the breakout session, we will resume this plenary session with more talks at 5 p.m. So please be back here. 5 p.m. Is that right? Please be back here at 5 p.m. Thanks.
Okay.